We left off in the notes and we were talking about types of different reactions. And again, after you've taken your quiz, you guys, if you're struggling with balancing equations, let me know. I can send you some more stuff to help you with that. Okay, so we talked about the first two. One was synthesis or combination, where you're taking stuff and you're combining them to make a product. We talked about decomposition, which is just the opposite. You take a substance and you break it down into smaller parts. Then the next type we're going to talk about is a combustion reaction. And a combustion reaction is when you burn stuff, okay? In the lab, if we were in the lab, when we light the Bunsen burner, we're actually burning propane. In North Dakota, we're big on propane, not natural gas. But that would be this one right here, okay? So when we burn when we light our little propane things, there's propane coming through here, and we add oxygen to it, and then we end up with carbon dioxide and water, okay? So anytime we burn, we do this. This is natural gas, this is propane, okay? So you take a carbon substance and an oxygen, and then you have to balance them out, all right? Now, when you're balancing them, you guys, when you're doing combustion, remember, do carbon first, then hydrogen, save your oxygen for last. If you do that, it's a lot easier. But it's really easy to tell if it's a combustion reaction. Look at your two products, carbon dioxide, water, carbon dioxide, water. Okay, so if you have carbon dioxide and water as your two products and your only products, okay, if there's something else in here, that's not combustion. But if you have carbon dioxide and water, you know it's a combustion reaction. That should be actually really simple to identify those types of reactions. Okay, and again, I don't have these. These are in your book. You can practice these. We'll talk about them later if you want to. Okay, all right. Then we have the replacement reactions. Okay, they put them in groups. I guess you could put them in as each individual, then we'd have 5 different types of reactions. But the difference between them, in a single replacement reaction, one element replaces another. If you look here, I have calcium chloride and lithium. What's going to happen is the cation lithium is going to replace calcium. So the two positives, the metals, are going to replace each other. So I end up with lithium chloride and calcium. Okay? And again, when you're writing these out, you guys, some people, because calcium's 2 here, they want to put LiCl2 here. It depends on what it's combined with. If you look, lithium has a +1 charge, calcium has a -1 charge. So that's why it's LiCl here, but it's Cl2 over here. Calcium's 2 over here, so that's why I have a 2 here. So make sure you write the proper formulas when you're balancing equations. But this is an example of a single replacement because what happens is lithium replaces calcium. Okay, chlorine still combined. Here it's calcium, here it's lithium. Okay, a double replacement is where you start with 2 compounds and you end with 2 compounds. In both cases, you're going to start with 2 and end with 2. But here I have 2 compounds and I end up with 2 new compounds. Here I have a compound and an element and I end up with a compound and element. That's the difference between single and double replacement. So if you look here, potassium goes with hydroxide and sodium goes with chlorine. So the 2 positive ions and the 2 negative ions switch partners. That's the difference between the 2. They'll call this a double replacement, double displacement, ionic, has all kinds of names. But really what happens is you start with 2 compounds and end up with 2 new compounds. And the way you can tell the difference between these two, look for a single element. If you have a single element on both sides, you know it's single. If you don't, it's double. Okay? Okay, so again, I want to review those really quick. If you're looking at equations and you want to tell which one is which, okay, a synthesis or a combination, you're going to end up with less parts than you started. Not amounts, but like I said, you might have 3 reactants and you only have 1 product. Okay? Or 2 reactants and you only have 1 product. You're going to start, you're going to have maybe 2 elements combine to form a compound. Okay, that's a synthesis. So you don't have the same amount. Like here, I have 2 reactants and 2 products. In a synthesis, I'm only going to have, I'm going to have more parts over here than I end up over here. That's how I know it's synthesis. They're not going to be the same on both sides. Decomposition is the same way, only now it's just going to be the opposite. I'm going to start with maybe 1 thing over here and it'll break down into 2 parts. Or I'll have 2 things over here and it'll break down into 3. So the numbers aren't the same on each side, okay? I'm not talking about balancing or anything. I'm just talking about, the number of reactants versus the number of products, okay? It's easy to tell combustion, carbon dioxide and water. If you have those 2, it's combustion, okay? And then single and double replacement, look, I have 2 and I end with 2. So I know it's either single or double. I have an element by itself, that's single. No elements by themselves, compound, 2 new compounds, then I know it's double. And that's the difference between those. So those are the 5 types of reactions, and it's actually not too hard to tell the difference. Just look at the difference between your reactants and your products. Okay, now we have compounds. It's easy to find the weight of an element. Boy, that was really loud. Sorry about that. An element's mass is on the periodic table. Well, what if we have a compound? Okay, well, actually, it's not so hard to tell when you're doing this. When we want to figure out the mass, now remember, they have their own kind of way of measuring. You can't really measure an atom or a molecule, they're too small. So what they did instead is they kind of made a system, it's in the right proportions, okay? But it's so that we can measure things using like a scale, okay? So we use AMU. AMU is atomic mass units. And we compare them, we consider them to be a gram if you want to measure things out. They're not. They're much smaller than that, but the proportion is the same, so it works. Okay? So atomic mass is measured in AMU, atomic mass units. We can convert them to grams. Okay? And there's the definition of it. It's 1 atom weighs 12 AMUs. If you look at carbon, its mass is 12. And since carbon is such a common substance, that's what they base it on. Okay? Okay? If you look on a scale, hydrogen has a mass of 1.008. If you guys just want to say 1, I'm fine with that. Oxygen is 16. And again, this is just the masses that are coming right off the periodic table. Okay, so what if we want to find the mass of a compound as opposed to an element? Like I said, element is easy. All you have to do is look it up on the periodic table. When we have a compound, we figure out its formula weight or its formula mass. It's the sum of all the atoms in there. Okay, so here's calcium chloride. So what I would do is I'd write, I have calcium and I have chlorine. I have 1 calcium and I have 2 chlorine. So you write the symbols, you write how much you have of each, and then you just multiply. And again, you guys, you don't have to use 40.08. If you want to use 40, I'm perfectly fine with that. Chlorine, you guys, is actually, when we write out or when we use it, its mass, we use 35.5. Okay, its isotopes just happen to fall in the middle. So if you take 2 times 35.5, you're going to get 71. So I take 40 plus 71, and I get 110.99. I'm just going to go with 111. Okay, you don't have to get so picky with these. All right, so formula weight is generally reported for ionic compounds. Molecular weight is reported for molecular compounds, like we talked about, if it's a metal and a non-metal, it forms an ionic bond. That would be formula weight. If it's 2 non-metals, that would be molecular weight. Is there any difference on how you find them? No, you find them exactly the same way. Okay, here's a molecular weight. And again, same deal. We're going to find the mass of C2H8. That's ethane. Okay, so I got carbon and hydrogen. I have 2 carbon and I have 6 hydrogen. Okay, well, and again, you don't have to use 12.011. You can just use 12. So 12 times 2 is 24. And 6 times 1, hydrogen is always fun to use because its mass is 1. So it's 6. So 24 plus 6 is 30. So the mass of C2H6, its molecular weight, would be 30. But again, you find them, formula weight and molecular weight, you find the same. Molecular weight is for molecules for covalent compounds, 2 nonmetals. And formula weight is for ionic compounds, a metal and a nonmetal. But you solve them exactly the same. You put down what you have, how much of each you have, and then you multiply by their mass. And again, you guys, you don't have to use these big long words. If you just want to use 12 and 1, that is totally fine with me. Okay? Calculate the formula mass of sucrose. So I'd go CHO, 12, 22, 11. Okay? So the mass of carbon is 12. 12 times 12 is 144. 22 times 1, yay, hydrogen is 22. And then oxygen, I got to make that one up. 11 times 16 is 176. So if you take 176 plus 144 plus 22, you get 342. Yep, it's a big molecule. It has a lot of mass to it. Okay, that would be a molecular compound because it's nonmetals. If I was doing this one, I'd have 1 calcium, 2 nitrogen, and 6 oxygen. Okay, anytime you have something in parentheses, you have to multiply everything inside. So calcium is 40, 2 nitrogen, nitrogen's 14, times 2 is 28, and then 6 oxygen, got my handy calculator here, would be 96. So I'd take 96 plus 28 plus 40. Okay, and it's 164. So when you're doing these, you guys, write down the symbols of what elements you have, how much you have, multiply by their mass on the periodic table, and again, you can round, and then add them together. That's all you do for formula weight and formula mass. Okay, same for these. Okay, I don't know if I need to do any more of those. Okay, that's how you find formula mass, formula weight, molecular weight. They're all the same. Okay, write down the symbols for your elements. So which you have, this one I'd have 1 aluminum, 3 oxygen, 3 hydrogen. Multiply by their mass from the periodic table. Aluminum is 27, oxygen 16 times 3, which would be 48. Hydrogen is 1 times 3, so you add those together. And yes, I know a lot of masses of the elements. I need to get a life, I know. But anyway, that's how you do it. Okay? So if that tells you the mass of the compounds, what if I want to know, let's say I have water. What percent of water is hydrogen and what percent of water is oxygen? Okay? Now, it might not be a big deal for water, but if you're a chemist and you work, like, let's say for a mining company, and you get coal, and you need to determine what percent of it is carbon, because the higher the carbon, the better it burns, the more BTUs or the more energy you get out of it. So you can actually figure this out. It's very simple. It's basically taking the individual mass divided by the total. If you do that, then you get your percent of each element. Okay, and here's the formula for it. It's probably better if I show you a problem. Okay, so ethane is C2H6. Okay, well, the first thing I'm going to do is find out its mass. All right, C2H6, there's 2 carbon. Okay, there's my 24. And then hydrogen is, it's H6, so 6 times 1 is 6. So the mass of ethane is 30. Okay, so if I want to find how much carbon is in ethane, I take the carbon's mass, which was 24, divided by the total, which is 30. And again, you guys don't have to worry about this. If you have 24 divided by 30, that's fine with me. Okay, so when I get my answer, I get 0.798887. I move the decimal over 2 because I want to change it to percent. So in ethane, which is C2H6, almost 80%, 79.89% is carbon. Not a lot of hydrogen. Hydrogen doesn't weigh much, so it doesn't take up a lot of space. Okay, so that's how you do percent composition. You take the mass of the element divided by the total mass. Do I have another one? Okay, if I was doing this one, calculate carbon, hydrogen, oxygen in C12H22O11. Okay, so in sugar. Okay, I can tell you the whole thing is 342. We did that already. So that's the mass of 12 carbon, 22 hydrogen, and 11 oxygen. So if I take 12 times 12, that's 144. This is the carbon. So if I take 144 divided by 342, I get 0.421, so 42.1% is carbon. Okay, for the hydrogen, I would take 22 and I divide by the total, 342, and I would get 0.064 or 6.4%. Remember, we've got to move that decimal over 2. And the last one, oxygen, the mass of oxygen in that is 176. And again, I got that 11 times 16. Okay, and if I take 176 divided by the total, 342, I get 51.5%. Okay, so that tells me the percent. So when you're doing percent, you take the individual divided by the total. Okay, when you're doing these, again, make sure when you're done, when you add up your totals, that they should be close to 100. If you get 99.9, that's fine. Or if you get 100.1, that's okay. But if you get 102, that's not so good. So make sure your percentages match up. Okay, here I did it here to show you. I took 12 times 12, which is 144, divided by 342, the total. I took 22 times 1, that's the mass of hydrogen, 342. And then I did 11 times this equals 176 divided by. So that's how I got it. Sorry, it's squished up there. We're just about out of time, so I'm going to leave you here. Talk to you soon.